Welcome back for 9.3 electrical power and energy. So when we talk about circuits and voltage and current, when we actually talk about them in our homes, we talk about the amount of power that we're using, and that's how we get charged by the company. So how is power related to a circuit? Well, first, we've actually talked about power and energy before in our energy unit, where we learned that power is related to a rate. In fact, we learned that power is the amount of time it takes us to do a certain amount of work, and we knew that work was related to energy. In electrical circuits, power is related to the rate that electrical energy is used in a circuit. So let's look at it mathematically. In circuitry, we can say that power is related to a voltage times a current. But we also know from previously that we can solve for voltage by doing a current times a resistance. Well, now we can take that and plug that in for V, and we can end up getting a new answer for power. If we substitute out V for IR, we end up getting I times R, which is actually I squared times the resistance. But then we also know that you could solve this around and you could solve it for I and get V over R equals I. Well, then I can plug this in for I, and I end up getting V squared over R squared times R, which will even out to be V squared over R. So I've gotten this nice long power equation from these two previous equations that we knew. Well, then I can take this a step further, and I can say that we know power is the work over time done by an object. Well, if I want to go from work and get power, all I need to do is multiply my power value by time, and I'll end up with work. So if we wanted a work equation, all we have to do is add time to each of these components. So first, power times time, I can do with our first variable, and I can do the same thing with each next step, VI times time, or I squared R times time, or our last equation, V squared T over R. All I've done is taken each of our power equations and multiplied by the time, because power times time will give us a work, or an amount of energy used in the circuit. Well, first, you see this nice equation that I just wrote out. You don't have to memorize it. It's on your reference table, and this is what it looks like on your reference table. The problem is there's a lot of different components. We have 4 things set equal to each other. Do we need to use each of those 4 things every time? Absolutely not. What you're going to do is look at the components you're given in a problem and decide 2 pieces of this long equation that you want to pick. For example, we could pick power and I squared over R and set those 2 things equal in an equation like this. Or we could choose power, set it equal to V squared over R, and get a brand new equation. All you need are 2 components out of this list of 4, and the same thing for work. So let's try a couple examples. First, we've got a 110-volt toaster oven that's drawing a current of 6 amps on its highest setting, and it converts electrical energy into thermal energy or heat. We want to know the toaster's maximum power rating. So let's talk about what I've got. I've got a voltage source of 110 volts. I know that the current is reading at 6 amps, and I'm looking for the power. Well, I know I'm going to use my power equation. Since I've got V and I, I'm going to use power equals VI. I'm going to plug in what we've got, 110 volts for V, 6 amps for I, and I end up getting a power rating of 660 watts. Think back, remember watts, the unit for power, but I also could have written that as V times A, or voltage times amps. Both of those are correct. Okay, so let's try another. We've got a potential drop, that's a change in voltage, of 50 volts measured across a 250 ohm resistor. I want to know the power developed. So we know the voltage is 50 volts. We know the resistance is 250 ohms. I want to find the power. So I'm going to pick the power equation that has voltage and resistance. That would be P equals V squared over R. I'm going to plug in what we've got here. We've got 50 volts, and that's squared, over our resistance, 250 ohms. And if you multiply that together, you get a nice 10 watts. Again, you could use the units V squared over ohms, which we would have come at from this, but power is measured in watts. And finally, Finally, if we have an electric iron operating at 120 volts and it's drawing 10 amps of current, I want to know the amount of heat energy delivered by the iron in 30 seconds. Well, let's write about what we've got. We know we've got 120 volts. I've got a current of 10 amps, and this is new. They've given us a time of 30 seconds. Well, actually, we're not looking for power in this case. We're looking for energy, which I know is the amount of work being done by the circuit. So I'm going to use our work equation that has V and I in it, VI, and I'm going to multiply it by our time to get a nice value. So 120 volts used at 10 amps for 30 seconds will give us the total amount of energy I'm using in that time, and that will be 36,000 joules. Again, remember, joules is our unit for work. You also could have said volts, amps, seconds, which is the same thing, but this is just simpler. And there's your example of using the components that I've given you here. What we're going to do in class and what you're going to do with your RG&E project is look at what these values actually mean. What is the energy used in a light bulb? What's the energy used in a dishwasher? And what do we know about power? So that's what we're going to explore in the upcoming lessons. Enjoy.